Welcome to our video on reinforcement learning in data science. Let's start by understanding what reinforcement learning is and why it's important. Reinforcement learning is a type of machine learning where an agent learns to make decisions through trial and error, receiving rewards for desirable actions. This self-learning capability is crucial in data science, offering advanced techniques to solve complex problems. From optimizing trading strategies in finance to enhancing robotics, the applications are vast. Throughout this video, we'll explore how reinforcement learning works, its key algorithms, and real-world applications. Stay with us as we dive into this fascinating domain that holds the promise of revolutionizing data science. Data science is a field full of challenges. From handling large data sets to making accurate predictions, the need for advanced techniques is ever growing. Whether it's managing the deluge of data or fine-tuning algorithms to deliver precise results, the complexity can be overwhelming. These hurdles underscore the importance of innovative approaches like reinforcement learning. When traditional methods fall short, cutting-edge techniques can provide the breakthroughs needed. In the upcoming segments, we'll explore how reinforcement learning not only addresses these challenges, but also revolutionizes data science. Stay tuned to see how this powerful tool can transform data into actionable insights and drive impactful decisions. Before diving deeper, let's quickly recap what machine learning is and the different types it encompasses. Machine learning involves algorithms that improve through experience, allowing computers to learn from data and make decisions without explicit programming. There are several types of machine learning, each suited to different tasks. Supervised learning involves training a model on labeled data where the outcome is known. Unsupervised learning deals with finding hidden patterns in data without predefined labels. And then there's reinforcement learning, where an agent learns by interacting with its environment and receiving rewards or penalties. Understanding these basics is crucial as we explore the role of reinforcement learning in data science. In this segment, we delve into the fundamentals of reinforcement learning, a captivating domain within machine learning. Reinforcement learning is about an agent learning to make optimal decisions by interacting with its environment. To begin, let's unpack some primary concepts and terms you'll encounter. In reinforcement learning, an agent is the learner or decision maker. The environment represents everything the agent interacts with. The agent performs actions which affect the state of the environment, leading to states, the different situations the agent may find itself in. A crucial element of reinforcement learning is the reward. This is the feedback the agent gets from the environment, indicating how good or bad the outcome of an action is. The agent's main goal is to maximize cumulative rewards over time. Another term you might hear often is policy. This refers to the strategy the agent uses to determine its actions based on the current state. Essentially, a policy maps states to actions. The concepts of value and value function are also integral. Value refers to the long-term reward expected from being in a specific state, while the value function helps the agent understand the potential future rewards of states and actions. Reinforcement learning revolves around an agent performing actions within an environment, receiving feedback through rewards, and optimizing its actions to achieve the highest cumulative reward. With these core principles in place, you're well on your way to understanding the foundation of reinforcement learning. Next, we'll dive deeper into how reinforcement learning works through exploration and exploitation. In the world of data science, reinforcement learning offers a powerful toolkit for solving complex problems. But how exactly does it work? At its core, reinforcement learning involves an agent exploring its environment to discover the best possible actions to take. During this exploration, the agent tries different strategies and learns from the outcomes of its actions. However, exploration alone isn't enough. There's a need for exploitation, where the agent utilizes the information it has gathered to maximize its rewards. Balancing between exploration and exploitation is crucial for the agent to learn effectively and efficiently. Too much exploration can lead to wasted efforts, while too much exploitation can result in missing out on potentially better strategies. This balance is maintained through a learning process that adjusts the agent's actions based on rewards and penalties it receives. Essentially, the agent is constantly evolving its strategies to improve its performance over time. This dynamic learning process is what makes reinforcement learning particularly powerful in dynamic and uncertain environments. Next, we'll discuss how this balance between exploration and exploitation plays out in various reinforcement learning algorithms. In the landscape of data science, one of the crucial aspects of reinforcement learning is understanding its key algorithms. Let's dive into three foundational algorithms that power this technology: Q-learning, deep Q networks, and policy gradients. First, we have Q-learning. This algorithm is based on the idea of learning the value of an action in a particular state. It enables an agent to learn the optimal policy by maximizing the expected reward through a trial and error approach. Q-learning is vital for tasks that require a balance of exploration and exploitation. Next, we explore deep Q networks, or DQNs. Building upon the principles of Q-learning, DQNs utilize deep neural networks to approximate the Q-value function. This allows for handling high-dimensional state spaces where traditional Q-learning would struggle. DQNs have been shown to perform exceedingly well in complex environments like video games, exemplifying the blend of reinforcement learning and deep learning. Lastly, we examine policy gradients. Unlike Q-learning and DQNs, which focus on value-based methods, policy gradients directly optimize the policy. This method is particularly effective when dealing with large action spaces or continuous action domains. Policy gradients refine the decision-making process by adjusting the policy parameters to maximize the cumulative reward. These algorithms form the backbone of many reinforcement learning systems, each bringing a unique approach tailored to specific types of problems. Understanding these key algorithms is essential to effectively implement reinforcement learning in data science projects. As we move forward, you'll see how these principles are applied in real-world scenarios. Let's look at how reinforcement learning is applied in robotics to solve complex tasks. Robotics often faces challenges such as unpredictable environments and the need for precise control. Traditional programming methods struggle to address these issues effectively. Reinforcement learning, however, offers a powerful solution by enabling robots to learn from their interactions with the environment. Consider a robot tasked with navigating a maze. Initially, it has no knowledge of the layout or best paths. Through reinforcement learning, the robot explores different routes, receiving rewards for making progress and penalties for hitting obstacles. Over time, the robot learns the optimal path to reach its goal efficiently. A real-world example of this is in the development of autonomous drones. These drones must navigate complex terrains and avoid dynamic obstacles, which require split-second decision-making. Reinforcement learning algorithms allow drones to learn these tasks through simulated environments, significantly reducing the risk and cost associated with real-world testing. Reinforcement learning has enabled robots to achieve tasks with greater precision and adaptability. In industrial settings, robots can now handle intricate assembly processes, which were previously challenging due to their complexity and variability. These improvements enhance productivity and open up new possibilities for automation in various industries. Next, you'll see another fascinating application of reinforcement learning in finance, where optimizing trading strategies and managing portfolios benefit from this innovative approach. Finance is an industry fraught with complexities and high stakes, where precision and strategy are paramount. Traditional methods of managing portfolios and creating trading strategies often come with significant limitations. But what if there was a way to optimize these strategies using advanced data science techniques? Enter reinforcement learning. This cutting-edge approach allows us to optimize trading strategies by continuously learning and adapting from real-time data. In reinforcement learning, we have an agent making decisions within a trading environment. Through a series of actions, the agent receives feedback in the form of rewards or penalties, learning the optimal strategies to maximize returns. Imagine a trading algorithm that doesn't rely solely on static rules, but evolves based on market conditions. By leveraging reinforcement learning, the algorithm can adapt its strategies dynamically, learning from past trades to predict future market movements more accurately. The results have been remarkable. Firms using reinforcement learning have seen improvements in portfolio performance and better risk management. These algorithms have shown they can navigate the complexities of financial markets, reacting swiftly to shifts and trends. The real power of reinforcement learning in finance lies in its continual adaptation. As new data pours in, the models improve, becoming increasingly sophisticated and fine-tuned. This translates into more robust trading strategies and better financial decision-making. Next, we'll explore its application in healthcare and how it's revolutionizing patient treatment outcomes. In healthcare, challenges such as effective treatment plans and improved patient outcomes are constant. Traditional methods often fall short in dynamic and complex scenarios. This is where reinforcement learning, a type of machine learning, comes into play. Reinforcement learning enables an AI agent to learn optimal treatment strategies through a system of rewards and penalties based on patient responses. By continuously adjusting treatments, the agent aims to maximize the cumulative reward, which translates to better patient outcomes and resource utilization. For example, consider a scenario involving pain management for chronic conditions. Through reinforcement learning, an AI can personalize treatment plans by learning from each patient's unique response to medication and therapy. In a recent study, researchers used reinforcement learning to develop adaptive dosing strategies for patients in intensive care units. This approach not only improved patient outcomes, but also reduced the risk of adverse side effects. These results demonstrate the potential of reinforcement learning to revolutionize healthcare, optimizing treatments in ways that were previously unimaginable. As we move forward, you'll see how reinforcement learning continues to make impactful strides in other sectors, addressing complex challenges with innovative solutions. Despite the vast potential of reinforcement learning, its implementation is not without significant challenges. First, the immense data requirements can be overwhelming, as vast amounts of information are necessary to train effective models. Second, the computational complexity involved can be a daunting barrier, often requiring specialized hardware and significant processing power. Lastly, ethical considerations cannot be overlooked. The development and deployment of reinforcement learning systems must account for fairness, transparency, and accountability. These challenges highlight the need for careful planning and robust solutions as we delve deeper into advancing this powerful technology. The future of reinforcement learning is incredibly promising. Emerging trends suggest even greater integration across various domains, pushing the boundaries of what's possible. Potential advancements are on the horizon that could revolutionize our approach to complex problems. As we look ahead, it's clear that the continuous evolution of algorithms and the growing availability of data will play crucial roles. Researchers are uncovering new methods that aim to enhance efficiency and effectiveness in unprecedented ways. Expect to see reinforcement learning applied in innovative fields, from autonomous systems to personalized healthcare solutions. These advancements will shape the landscape in our daily lives. Reinforcement learning can be a powerful tool in data science projects. Let's look closely at how integrating this technique can transform your workflow and outcomes. In data science, reinforcement learning brings a dynamic to solving complex problems that traditional methods may struggle with. It provides the ability to learn continuously from new data and adapt to changing environments automatically. To better illustrate how reinforcement learning is being successfully integrated into data science projects, let's explore some real-world examples. In the realm of supply chain management, reinforcement learning is used to optimize logistics. Companies like Amazon utilize it to streamline their inventory management, forecast demand, and route deliveries more efficiently. Another fascinating example comes from the healthcare sector. Here, reinforcement learning algorithms assist in personalized treatment plans. They evaluate patient data continuously, updating recommendations based on new information, ultimately leading to improved patient outcomes. E-commerce platforms also leverage reinforcement learning to enhance customer experience. Personalized recommendation systems learn from user interactions, offering more relevant product suggestions over time, which boosts sales and customer satisfaction. These examples highlight the versatility and potency of reinforcement learning in diverse domains. By integrating these models, data scientists can tackle more complex problems, allowing for smarter decision-making and more efficient resource management. Next, we'll cover key resources that can enhance your understanding and proficiency in reinforcement learning. When venturing into reinforcement learning, choosing the right tools and libraries is crucial. TensorFlow and PyTorch stand out as two powerful frameworks for developing and training reinforcement learning models. TensorFlow, developed by Google, offers robust support for deep learning, and PyTorch, favored for its dynamic computation graph, is widely used in research. Additionally, OpenAI Gym provides an extensive toolkit for developing and comparing reinforcement learning algorithms. This rich ecosystem of tools and libraries simplifies the process, enabling you to focus on crafting effective models that can tackle complex problems. If you're interested in getting started with reinforcement learning, there are plenty of resources available to help you take your first steps. Online courses, such as those offered by Coursera and Udacity, provide structured learning paths. Books like Reinforcement Learning and Introduction by Sutton and Bartow give comprehensive insights, and tutorials available on platforms like GitHub and YouTube can help you practice coding real-world examples. Start with understanding the basics, dive into projects, and don't be afraid to experiment. Reinforcement learning is a journey, and the best way to learn is by doing. As we conclude our journey through reinforcement learning in data science, let's take a moment to recap the key points we've covered. We explored the fundamental principles and important challenges that reinforcement learning helps to solve in various domains, including robotics, finance, and healthcare. From understanding core algorithms like Q-learning and policy gradients, to recognizing the future potential and advancements in the field, reinforcement learning stands as a powerful tool. Thank you for staying with us until the end. Up next, we'll tell you how to continue your learning and stay updated with the latest in data science and machine learning. Thank you for joining us on this journey through reinforcement learning in data science. If you found this video insightful, please consider subscribing to our channel. We're committed to bringing you more in-depth content on data science and machine learning. Don't forget to hit the notification bell so you never miss an update. Follow us on social media for the latest trends and tutorials in the field. Your engagement helps us continually improve and tailor our content to your needs. See you in the next video.